Okay, last time we have been working between rendezvous problem between two vehicles in circular orbit. So, we continue with that, little bit was remaining. So, I will cover it and then we will go into the elliptical orbit. Okay. So, the problem started with that we have two vehicles located at A and B, and angle between A and B was given to be phi a b, and what was required that while B moves along the orbit shown by the blue line. So, once it reaches the C, so the new position of the B is then shown by B prime, which is coinciding with C. So, at that time A has to reach at C and catch it up. Okay. So, for catching it up, it has to be sent in some faster orbit, because naturally here the time taken from going from this place to this place, whatever is there. So, if it matches with this, then only it is possible. If it goes along the original orbit, then it is never possible, because it will always keep traveling by the same angular distance. Okay. So, neither we saw that we saw that it is not possible to go along this, because these are going to take much longer time, this is also not possible. So, ultimately we decided to send it along this orbit, and then we have started working in this direction. So, what we wrote a number of steps. So, in those steps involved were, the first one was assume eccentricity of the orbit E of the transfer orbit, then calculate E equal to r y, or here plus minus we can write to minus r b square by mu. This is plus for ellipse and minus for negative sign for hyperbola. So, if your trajectory is ellipse, then the plus sign will be used. If your trajectory is hyperbola, then the negative sign will be used, where E is the semi major x. Okay. And also here the theta 0, which is the perigee position known. So, here in this step r v square by mu, this can be calculated using the relation that we developed earlier. So, we can state it here again. Okay, and therefore, A will be available. So, once A is known, then calculate TAC, compare TAC with TBC. If TAC equal to TBC, then assumed value of E is correct. Otherwise, revise the value of E, and this process has to be iterated until T A equal becomes T A C becomes equal to T B C. Okay, so, this ends the process for. So, the otherwise revise the value of E, and repeat from step 1. Okay. So, if this process is carried out repeatedly, then you get the desired solution. So, the solution we already worked out last time. So, now we go into the elliptic orbit. So, rendezvous between two vehicles in elliptic orbit. So, we have rendezvous between two vehicles in elliptic orbit. Now, suppose two vehicles are there, which are A and another one is located at B. The focus is located here, and A has to catch up B at some location, say C. So, A has to catch B at some location C, which is given. Okay. So, here we have this angle is phi a b and this angle we write as phi b c. Okay. Now, to catch up B at C, so A must move faster than B, and therefore, let us say that it has to be sent along a different orbit. And perigee position for the transfer orbit is shown by this blue lines. Okay. So, the position from here to here, the angular position of the OA, it can be shown by theta a. Similarly, the angular position of C can be shown as theta c. So, we have angle AOB, this is equal to phi AB, angle BOC equal to phi BC, and we will write phi as phi AB plus phi BC, and this will be is nothing but angle AOC. So, let the transfer trajectory be shown by the curved blue line as shown in this figure. This is the curved blue line. So, this is the transfer trajectory. So, we now need to proceed in the same way as earlier we have done, but the earlier the case was little more easier in that the theta 0 that we computed, if you look into this the earlier figure in the circular orbit. So, this theta 0 became known because this whole angle was known, and therefore, we divided and got the perigee position here in this place. But here in this case it is not easy to do that, it is not possible using working this policy will not work actually here in this place, because it is elliptical or maybe the hyperbolic orbit in which you are sending it, and it is a faster orbit. So, here the theta a need to be assumed. Okay. So, assume theta a. Okay, and then we can use equation L by r is equal to 1 plus e cos theta. So, for the once the satellite is here, so for this position we can write L by r a equal to 1 plus e cos theta a. Similarly, we can write L by r c equal to 1 plus e cos theta c, and this is in the transfer orbit. And you will put the subscript here t to indicate that this is the transfer orbit, and maybe you can put here t also to indicate this is the semi lattice rectum of the transfer orbit. Here theta a, this is the assumed perigee position. So, from these two equations, let us say this is equation number 1 and this is equation number 2. So, from equations 1 and 2, we can write R A by R C one plus E t cos theta c divided by 1 plus E t cos theta a. Now, theta c, this can be written as theta a plus the angle AOC. So, AOC we have written as phi. So, we will add up here in this place, okay, and insert into this equation. So, this becomes 1 by E t cos theta a plus phi by 1 plus E t cos theta a. So, this is our equation number 3. In this equation, theta a is assumed. So, known, therefore, this is known, but maybe it is a wrong value, but it is a known now once you have assumed. Okay. Phi is known, R A is known, and R C is known. Because the elliptic orbit is given to you and the position of R A and R C may be given in terms of the true anomaly of the original elliptic orbit, which is shown here by the blacking. Okay. So, from here it is possible that we can compute the value of E t. So, from equation 3, so solve equation 3 to or simplify equation 3, we write simplify, get E t. So, if we do that, so this will be R A plus R A E t cos theta a, this is equal to R C plus C E t plus phi. Therefore, this implies R C minus R A R C E t cos theta a plus phi, and E t we can take as common. and this implies E t equal to so this is our equation number 4, which gives the value of E t. So, here R A, R c, theta a and phi, all these are known, and therefore, E t can be computed. So, now the steps for computing the transfer orbit can be written as assume theta a and assume theta a, phi is known, this is given. Find E t, the eccentricity of the transfer orbit, using equation 4. Okay, that is, you need to equate using R c minus, for known theta a, phi E t, calculate R a V a square by mu phi a, the flight angle at A, then R c V c a square by mu and phi c So, R a V a square by mu this can be written as 1 by 2 E t cos theta a Similarly, R c V c a square by mu. So, this you are writing for transfer orbit. A plus phi cos theta a plus phi find semi major x of the transfer orbit. So, this will be given by a plus minus r by 2 minus r b square by mu, where plus sign for ellipse. So, if your E is turning out to be less than 1, okay, then you need to choose the plus sign, and if your E is turning out to be the E which you have calculated in the second step. Okay, so, if it turns out to be greater than 1, means hyperbola, then you need to choose a negative sign in this equation. Now, phi a and here whatever we have written phi a, and so we will write this as flight path angle at A, flight path angle at C. So, we will see that how the flight path angle to be indicated in this case. We will do at the end after writing all the steps. So, step number 5 we have now calculate TBC from the earlier discussion for the circular orbit. And it is easy doing, calculating TBC means in the original orbit how much time B is going to spend to go from B to C. So, this we are writing as TBC, and then also you need to calculate along the trajectory, transfer trajectory, this TAC. So, compute TAC also. Now, because the eccentricity is known to you, semi major axis you have calculated for the transfer orbit also. Okay, this position already you have assumed, and therefore, from this position to this position, going from this position to this position in the transfer orbit, how much time will be required, that is indicated by TSC, can be computed exactly in the same way. So, for calculating TBC is easy, but for computing TSC, what you need to do? So, first point TA in transfer orbit, and then find TC in transfer orbit. Okay. And measuring from P. Okay. So, this implies that you find out how much time it will be required to move from this place to this place, and how much time it is required to move from this place to this place in this transfer orbit, and then subtract. Okay. So, once you subtract, so TSC will be equal to T c minus T a. So, once you have done this, so compare T a c and T b c. This step is important. Okay, once T a and T b c you are comparing, so next step we can write if in the same step let us write if T a c equal to T b c, then chosen value of theta a is correct. Otherwise, it is incorrect. So, if it is incorrect, so as a next step, if T a c equal to T b c, then stop. Otherwise, go to step 1. So, now you can see that if T a c equal to T b c, then your assumed value of theta a is correct. Okay. And once theta a is known, then obviously E t can be calculated, the semi major axis can be calculated. If it is not correct, then go to the step 1, assume theta a again and iterate in the same manner, and therefore, you will be getting the required value of theta a after some iteration. Okay, now let us finish. We have done this earlier also, but I will revise it here. Say this angle is theta 0 and this is the center of attraction, and we are measuring r along this direction. So, this is our r. Suppose this is the velocity vector at this position, and this is the trajectory, and velocity vector is tangent to this. So, this is called the flight path angle, which we write as f p a. So, V can be broken into two components, r dot in this direction and theta dot times r in this direction. And H we can write as r cross V magnitude, okay, where the angle between this and this is 90 minus phi, and also earlier we have written in terms of alpha. So, it is a multitudes of ways are there in which you can write. So, this is r times V sin 90 minus phi is equal to r V cos phi. Okay, so, here we know that H is equal to mu times L under root, or and therefore, H square by mu we can write as L. So, L herein we can replace this as H square by mu r equal to 1 plus E cos theta, and H square from here again we can insert r square V square cos square phi divided by mu r equal to 1 plus E cos theta, and therefore, r V square cos square phi by mu, this becomes 1 plus e cos theta. Now, taking again this equation r is equal to L by E plus cos theta. So, we have r dot equal to L by L times E cos theta whole square times C times sin theta into theta dot with a minus sign here. Now, here in this equation we can do little bit simplification. So, this can be written as r square by L times E sin theta times theta dot. So, what we have done here, multiply the numerator and denominator by L. So, this becomes L square and the below you have 1 plus e cos theta square and you will have L term here. So, from here we can see that L by 1 plus e cos theta is equal to r, and therefore, that becomes r square, and denominator whatever the L is there, and that comes, and then obviously, we have these terms here. Now, we can see that tan phi, this is given as r dot by r times theta dot. Here this is the angle phi. So, tan phi will be, this is f p a, we can write this f p a. Okay. So, this distance divided by this distance. So, in this direction we have theta dot r, and here this is r dot, okay, component of B. So, r dot, just now we have got r square E sin theta times theta dot divided by L, and then sin theta times theta dot. So, theta dot we write here, and then we have 1 by r times theta dot. So, this will cancel out theta dot term, and what we get r E sin theta by L, and from here you can see that r by L is nothing but 1 plus e cos theta. So, this becomes E sin theta divided by 1 plus e cos theta. This we are using here in this place. So, this flight path angle, this is necessary to calculate, and it is always required. Okay, and therefore, r v square by mu e cos theta and 1 plus, this we can write as r v square by mu is equal to 1 plus e cos theta divided by cos square phi, and this we can take above, this is sec square phi. One plus tan square phi Okay, here this term will cancel out, and here these two terms can be added to give E square. So, this becomes 2 E cos theta plus E square by 1 plus E cos theta. So, this equation plays a major role in finding out the value of R v square by mu given the true anomaly theta. This is nothing but the theta which is appearing here, this is nothing but your true anomaly. So, once the true anomaly is known, E is known, and therefore, R v square by mu can be calculated. And this R v square by mu, this is required in calculating the semi measure x, which we have always written as plus minus 2 minus R v square by mu. So, once you get the R v square by mu, so therefore, A can calculate. So, in all the process does we see that either we have to assume the some eccentricity as we have done in the circular case, or either we have to assume the perigee position and then utilize the relevant equation to get the value of the eccentricity. So, by this process we are able to work out the desired transfer orbit in which the satellite should be sent to do the rendezvous job. And of course, when the satellite reaches near the, so this is precisely theoretically what we do, but in the actual orbit, let us say once the satellite reaches near the another satellite, then a precise maneuver using the camera is done, and then the rockets are fired and there are cameras. So, exactly whatever the requirement is there, that is used to dock the two satellites. So, many missions you might have heard that the one satellite is docked to the other. So, this is done using this technique. So, thus we have computed all the relevant informations for rendezvous in two orbits, either be it the circular or be it the elliptical orbit. But till now whatever we have discussed, this is all about the coplanar transfer. Okay. Now, the question arises, what if we have the non coplanar transfer. So, for non coplanar transfer we have little more complicated steps involved, but the procedure will remain same. So, we will go through the non coplanar maneuver to do the rendezvous between two vehicles which are moving in two different orbits. Between two non coplanar orbits. So, the question now arises, why it is so important to do this non coplanar maneuver. There are various reasons for that. So, let us first go into that. Non coplanar maneuver. So, as the meaning implies, the two orbits which are not in the same plane. So, this will change the inclination of the orbit, and it will change the ascending node, or what we have written as the nodal angle. Now, if we look into this the coplanar maneuver. So, in the coplanar maneuver what we did, either we had the elliptical orbit or the circular orbit. Okay, so, the case where we are inside may be the circular orbit and then we have to go into the outer orbit which is elliptical one, or both are elliptical. Okay. So, in such cases if you give impulse here in this place, okay, if you give here impulse in this place. So, what exactly you are doing? We are just changing semi measure x. One, the second thing what we are changing, eccentricity. Okay. So, this will be always the case that if we are applying the impulse either at the apogee or the perigee. So, if we say this is our focus f. So, if we apply the impulse here delta v, okay. So, then we are going to boost up the apogee position. So, apogee will move from here to here. On the other hand, if we apply the boost here in this place, let us say let us apply in this direction. So, if we apply here in this direction, so then we are going to boost it the perigee position. Okay. So, perigee, this is the perigee position which will move to p prime. On the other hand, you can apply the impulses at different points in the orbit other than apogee and perigee. If you do that, then what will happen? So, depending on the impulse, your semi measure x a, the eccentricity e, and the argument of perigee a small omega, this is argument of perigee. Thus, the coplanar maneuver, we can see that it is able to change the semi measure x, the eccentricity and the argument of perigee, and all these quantities they lie in the same plane, and that is why it is called the coplanar maneuver. So, coplanar maneuver only can change the coplanar quantities, it cannot change the non coplanar quantities which are characterized by the angle of inclination I and the nodal angle. So, this is x, y and z, this is inertial reference frame. This is the center of the force. Here we can show by this green line the projection of this orbit on the x y plane. So, the dotted green line projection of orbit in x y plane. Okay. So, angle between this projected line or the xy plane and the orbit, this is your angle of inclination, and this we have written as the ascending node and this is the descending node O prime if the satellite is moving in this direction. Okay. So, you have the angle of inclination and the nodal angle then we showed as angle from here to here. Okay. Argument of Parisi we showed as p here in this place. So, this was the Parisi position. So, argument of Parisi was shown like this omega, and then you have the satellite in the orbit in some place here whose radius vector is r. So, this angle was shown to be the true anomaly. So, what exactly we are doing in the coplanar maneuver? We are just doing the maneuver in the plane of the orbit, okay. While the non coplanar maneuver, it is a concern with changing the capital omega or the nodal angle. This is your nodal angle and this is I, which is your inclination. So, the our next topic of interest is, as we stated earlier, rendezvous in two orbits which are non coplanar, and these two orbits can be either circular, both can be circular or both can be non circular. Okay. Either one can be circular, another can be elliptic. But the thing is that the whole philosophy is that whatever we have discussed earlier, the same analogy will apply here. Only thing we have to cautious about that out of plane. Now, the in whichever orbit the actually the satellite is moving and it has to catch up another satellite in a different orbit which is non coplanar with it. So, out of plane impulse now need to be given. So, those how much will be the value of or what quantity of the out of plane impulse need to be given, that must be computed in a proper way. So, now the question arises why there is a need for the non coplanar maneuver. So, the need arises because we can see from a diagram say this is the equator of the earth. This is the pole P, this is the pole P. Okay. This is the center of attraction or center of the orbit of okay. So, this is your equatorial plane. Now, suppose this is your earth and take another latitude. So, we will indicate this by this line from here to here. And let us say this the latitude of this point, this is lambda. Now, suppose you are in this point. Okay. So, if you are in this point and this lambda value may be say 40 degree 45 degree or 30 degree, or even it may be towards the pole. So, lambda is not equal to 0. So, if lambda is not equal to 0, so in that you can see that the satellite launch can be done only in the along the diameter of the earth. So, we have number of diameters here. So, this is the equatorial circumference. So, we will have the non equatorial circumference, which can be shown by say okay, it can be shown by this line. This is the non equatorial circumference or non equatorial circle around the earth. Okay, so, figure is not very good, but bear with me. So, here you can see here if you are here in this place, you cannot launch the satellite along this direction. It is not possible, because once you launch in this direction. So, there will be a component of gravitational force which will be acting vertically down, and it will deorient from this place to this place. Okay, so, this is not a proper direction. So, which is the proper direction? This is our proper direction of launching. So, we launch along this direction, okay, and let us say that earth moves from west to east in this direction. So, it is a rotating anti-clockwise here in this direction. Okay. So, if you launch it in this direction, okay, so you can see that this direction is actually making here the angle I. This is the angle that it makes with the equatorial plane. Okay. So, in the beginning itself, at launch, you get I not equal to 0, while your requirement may be that I should be close to 0 or maybe 0. Okay. So, this requirement you know it very well, that for the geostationary satellite or for the geosynchronous satellite, this angle of phi either it should be 0 or should be small. So, that the north south drift is less. Now, if such condition arises, then naturally you need to transfer it from this orbit to in a orbit. So, this is just the projection of the orbit on the earth. Okay. Similarly, we can have a equatorial orbit. So, we can take the projection of that orbit on the earth, and which is showing here as the equatorial circumference. Okay. So, this is also called the ground track. So, if your situation is like this, then you need to give impulse in this orbit. Okay. We can give impulse once it reaches here. So, we can give impulse here in this place to transfer it from this orbit to this orbit. So, various ways. So, here the non coplanar maneuver is there, and this maneuver is very simple, because both of them are here in it is in one orbit, another one is another orbit which is just rotated, but we will have multitudes of complicated conditions rather than this one, and we need to tackle that. So, we will do rest of the work. We will start with a fresh work for the non coplanar maneuver in the next class. So, thank you very much for listening.